Hello everybody, I'm Mango Thunderslice, and today is Ether Physics 202, the 1919 Eddington-Einstein Eclipse Fraud. This is going to be a good one. I'm actually still preparing for Ether Physics 203. This is going to be kind of an intro to that. We're going to be looking at the most effective challenge to Ether Physics 101, the Man Who Disproved Einstein, all about Dayton Miller and his results back in 1933, measuring differences in the speed of light corresponding to where the Earth's position is around the Sun over the course of the sidereal calendar, aka the year. And we're going to be looking at that challenge to Dayton Miller, which is a pretty good article. Then we're going to be looking at another article about the 1919 solar eclipse, which was the singular pinnacle event which launched Einstein from relatively unknown, just crazy-haired little nobody working in a patent office to an absolute scientific celebrity, you know, the highest, most well-known scientific icon and persona that the world has seen. And it all came down to the 1919 Eddington-Einstein Eclipse. So we'll just go ahead and jump into it. All right, an explanation of Dayton Miller's anomalous ether drift result by Thomas J. Roberts of the Illinois Institute of Technology in Chicago, Illinois, as well as Muons Inc. in Batavia, Illinois. And just real quick to examine who this guy is and what Muons is, I looked him up. Basically, they make, it looks like they're making the fourth generation nuclear reactors, right, using actual spent nuclear fuel to produce power. You know, it looks like these guys are doing some pretty cool work, and furthermore that Thomas Roberts is a pretty smart guy. But yeah, there's their website showing basically some of the technology they're working on. And yeah, Tom Roberts is their VP of Computational Physics, PhD. He's a scientist, and he spent 17 years in experimental high-energy physics and 24 years as a distinguished member of technical staff at Bell Labs. He's a physicist and computer scientist with broad experience in all aspects of software development, systems architecture, and computational physics. Right, so he is a pretty smart guy, and I'm not going to spend any time trying to detract from his credibility. This is the most effective rebuttal to my Ether Physics 101 video that I have encountered. A viewer brought this forward, and I congratulated him. I love to have this whole point of making these videos, guys, to have the conversation, not just to tell you what the truth is, because I'm on the search too, right? So anyway, very smart guy, and we'll just get into it, right? Here's the abstract. Essentially, in 1933, Dayton Miller published the results of his voluminous observations using this ether drift interferometer, proclaimed that he had determined the absolute motion of the Earth. And this result is in direct conflict with the prediction of special relativity, and also with numerous related experiments that found no such signal or absolute motion. This paper presents a complete explanation for his anomalous result by A, showing that his results are not statistically significant, B, describing in detail how flaws in his analysis procedure produced a false signal with precisely the properties he expected, and C, presenting a quantitative model of his systematic drift that shows there is no real signal in his data. Right? And so this basically is, he's saying that to summarize, and I'll get into it in a second, he's saying that basically there are anomalies within Miller's data set that are fairly large relative to the signal which he claimed to measure. And so if you actually put error bars around that signal and his data, he's claiming that the signal is not statistically significant. And his math looks good, but he's got some logical errors, which I'm going to point out in the course. So we'll just get into it. So yeah, Dayton C. Miller's 1933 article in this journal reviewed the results of his voluminous measurements obtained from his ether drift interferometer and proclaimed to the world that he had determined the absolute motion of the Earth. This claim has been embraced by some, rejected by many, and remains controversial today. Unfortunately, acceptance or rejection of Miller's result has been based primarily on whether or not it conforms to a person's prejudices and not on any solid objective criteria. Shankland et al. Attempted to address this situation by re-examining Miller's data. Unfortunately, they did not fully resolve the issue because they merely showed a correlation between signal and temperature drift, but did not give any argument or discussion of how that could generate such a remarkable result. Posthumously, Miller is now experiencing every experimenter nightmare. The standard analysis algorithm used by himself and all his contemporaries had serious flaws not explicable for many decades, and they caused the noise in the apparatus to perfectly mimic the signature of a real signal. This paper provides a detailed and complete explanation of his anomalous results, giving solid and credible reasons to reject Miller's claim. A basic error analysis of his results shows that they are not statistically significant. B, his analysis algorithm has serious flaws that force the noise in his data to precisely mimic the properties he expected in a real signal. And C, a quantitative model of his systematic drift accounts for 100% of his usable data, leaving no real signal. This reanalysis of his data puts an upper limit of 6 kilometers per second on the absolute motion of the Earth, which is fully consistent with related experiments and the prediction of special relativity. Miller took his data and analyzed them as follows. The interferometer was set rotating slowly and was adjusted so the fringes were visible, with the center fringe near the center of the field of view. Right, so he's measuring the variance of the speed of light by the fringe position, the movement of the intersection of the two light beams. Right. There is a small pointer affixed to one of the mirrors, and a central fringe position is visually measured relative to it in tenths of a fringe width. The observer walked slowly around a circle, watching the image in the telescope. There are 16 markers spaced equally around the circumference, and the observer called out the position of the central fringe at each marker. An assistant recorded the values. Miller expected the real signal to be a sinusoid with a period of half turn, with its amplitude related to the speed of absolute motion and its phase related to the direction. The ease of seeing a signal in these data is illustrated in Figure 1, which shows a plot of his signal at the bottom, and we'll get to those. That plot quite clearly shows a reasonably sinusoidal variation with a period of 1/2 turn, and it certainly looks like Miller expected a real signal to look. But that is a plot without error bars, and one cannot determine if that variation is statistically significant or not, so we must consider the errors in this measurement. The first thing to do is look at the data of Figure 1, plotted in Figure 2, which shows the raw data with adjustments restored. This is a huge variation, about 100 times larger than the amplitude of the plot at the bottom of Figure 1, and extracting any signal from such a large background is a challenge. Clearly, the interferometer systematically drifted about 6 fringes during this run, as the large-scale changes cannot possibly be any real signal with a period of half turn. From the way data were recorded and from Miller's own estimates, the statistical errors in these data are on the order of 0.1 fringe. So both the size and the shape of the variations in Figure 2 imply that this is a large systematic error. For instance, all measurements in the last turn are systematically almost 6 times smaller than those in the first turn. Right, so over the course of the experiment, what the data show is that there was a large systematic drift of where that center intersection of the light beams was, and this was very consistent that over the course of the runs, right, it would drift further and further systematically. And so what Tom Roberts has done is kind of tried to reduce that and subtract it out. And so anyway, going on. While Figure 3 shows the inadequacy of assuming a linear drift, it is still useful to obtain quantitative error bars for these data analyzed in this manner, because this is what Miller used to obtain his results. A general rule for error analysis is that when averaging raw data to obtain a value, one can histogram the data to obtain the corresponding error bar. Each point in the plot at the bottom of Figure 1 consists of the average of 40 readings, 2 marker values 180 degrees apart for each of 20 turns of the interferometer. The other data reduction steps do not affect the error bars significantly, except by scaling it. The 8 histograms corresponding to these averages are unremarkable, look reasonably Gaussian within their statistics, and have sigmas of 0.7 to 0.8 fringes. Right, and we'll get to that. That number is significant. We'll get to that in a second. But anyway, continuing on. But these variations are dominated by the systematic drift displayed in Figure 3, and for such systematic effects, the sigma of the histogram corresponds to the error bar. So here he's basically saying that the error bar for the experiment is 0.7 to 0.8 fringes. Since Miller's day, our attitude towards experiments like this has changed, and now we use them to test theories rather than to determine the absolute motion of the Earth. And we do this quantitatively using x-squared fits or similar. So the modern approach to interpreting these data in Miller's theoretical context would be to start with Miller's model of absolute motion as applies to his instrument and test the class of theories. The Earth is moving with absolute speed x in direction y, where x and y are determined by fitting determined by fitting to the data. The speed x is related to the amplitude of the signal and the direction y to its phase. So, right, depending on which side of the sun we are, which notices the biggest variance, that would indicate that's where the biggest ether wind is coming from, right? And how big the amplitude is, right, how big of a difference in the speed of light we're measuring would seem to indicate how fast that wind is moving. And, interpreted another way, not just the wind flowing, but us moving through it. Just like, a car moving through space, you're going to feel wind if you put your head out the window. Anyway, continuing. The speed, Miller's conversion from signal amplitude to absolute speed is given in Figure 20 of Miller 1933, in which 0.7 fringe corresponds to 24 kilometers per second. But all runs in the data sample have the property that the error bars exceed the variation in the final half-turn plot, as in Figure 4. That means that this analysis cannot really determine the direction of absolute motion at all, and cannot say very much about the speed other than it is less than about 30 kilometers per second. Miller in 1933 displays several plots of absolute speed and direction, but they are all without error bars. Had he computed and plotted error bars as above, they would be so large that in no case would they fit on the plot, and would often not even fit on the page. His determination of the absolute motion of the Earth is not statistically significant. Considerable insights into the effects of the data analysis procedures is obtained by considering a Fourier transform of the data and procedures. The data were manually sampled at a rate of 16 samples per turn with a resolution of 0.1 fringe. In modern terms, the human observer was performing the function of a sampling analog to digital converter. And so basically he reduces all of the data down kind of to a elementary statistical analysis of each position around the circle of the interferometer and what the variances were, and basically just pouring those into a different tallying and analysis system than Miller himself was using, and really didn't even exist back in 1930s, right? And so he kind of explains where a real signal would be, and based on these frequency bins. So he says there's a small bump in frequency bin 40, which corresponds to a period of half turn, and any real signal would be in that bin. We will come back to it. There are three basic flaws in Miller's data reduction algorithm. A, averaging the data, B, assuming the systematic drift is linear, and C, absence of a quantitative error analysis. These were not considered flaws in Miller's day, and all experiments of this type were analyzed with minor variations of this algorithm. Together with his rather large systematic drift, however, they permitted Miller to be fooled into thinking there was a real signal present. In the next section, a new analysis is presented which avoids all of these flaws. In Miller's day, the ideas used in the above discussion were not well known or fully developed, and it's not surprising that he was fooled. Today we know that the averaging of data during analysis should be avoided whenever possible, and one should of course use the full 320-point DFT of Figure 5. That spectrum clearly shows that the low frequency bins, corresponding to a slow systematic drift, completely dominate any real signal. Unfortunately, this approach is not able to determine whether the content of frequency bin 40, period half turn, is a real signal or due to the systematic drift. Doing that requires an accurate model of the systematic drift discussed next. So, and there's the formula. Essentially, he explains how he kind of reanalyzed this. And basically, he goes into it. These data display frequent instabilities, including occasional drifts of more than 2 fringes per turn and occasional jumps as large as 1.5 fringes between successive markers. One run drifted by 18 fringes in 17 turns, but then 3 runs drifted by less than 1 fringe during 20 turns. Right, so there was a wide amount of variance. Sometimes the light beam would be way off, during several consistent runs, and then other times it would seem to stay stable. Right, so and Tom Roberts is saying, see how crazy these variations are. I mean, these are errors in your system. You have to correct for these, and if your signal is smaller than them, then it doesn't exist. Right, that's the basic logic of his claim. As this analysis concludes there is no signal in Miller's data, it can set an upper limit on any signal with period half turn and the absolute motion of the Earth. From Figure 11, omitting runs with open circles as discussed above, a reasonable estimate of the overall error bar is 0.015 fringe for all sidereal times and all epochs of data. The error bar is dominated by the systematic drift, and the availability of many runs does not decrease it. That implies an upper limit of 0.025 fringe at the 90% confidence level. All right, and we'll stop right there because that number that he told us up before, which was 0.7 or 0.8, right, he's now given us three essentially different error bar values, right? He gave us 0.7 or 0.8, right? We'll just call it 0.8 up above, and now he's giving us 0.015 and 0.025. And he says that the 0.025 error bar, 0.025 fringe as an error bar has 90% confidence level, statistically speaking. So that's kind of strange in and of itself. He's given us two widely divergent error bar values in his analysis, and so that's confusing. I don't see anything else in this article to explain why that is the case, except for this next sentence, which is, maybe I'm just not smart enough to understand what he's talking about because it's not explained, and as far as I'm concerned, I don't care how smart you are. If you don't explain your statements, they're not intelligent. But so this is the sentence. This must then be increased by 1 over cosine, latitude, to account for the worst case projection onto the plane of the interferometer. I just simply have no idea what he's talking about there. If somebody can explain that to me, perhaps unravel my whole thing here, that would be great, because I simply cannot decipher what in the hell he's talking about with that sentence. Perhaps what he's talking about in that sentence, multiplying these numbers by 1 over the cosine of latitude, maybe that multiplies those numbers, several times over and puts them up at the 0.7 or 0.8. Anyway, that's all I can figure out because, again, he's given us three different values for this error bar, and it's very significant to the entire point of this article. Anyway, continuing. Figure 20 of Miller in 1933 relates fringe shift to his model of absolute speed, yielding an upper limit on the Earth's absolute motion of 6 kilometers per second, 90% confidence level. This value is consistent with similar experimental measurements and with the null result predicted by special relativity. Okay, and then there's the conclusion, essentially. This paper has not only explained how Miller was fooled, it has also presented a reanalysis of his data. This new analysis shows there is no significant signal in his data and puts an upper bound on the absolute motion of the Earth of 6 kilometers per second, 90% confidence. This is fully consistent with similar measurements and with the null result predicted by special relativity. I guess I'm repeating myself, I just said that, but anyway, he goes on to talk about some of the other, he talks about Michelson-Morley, he talks about other interferometer experiments such as Illingworth. And it's very interesting. I thought, just to clarify a point we'll get into in a second, he says, this innovation in this interferometer is a 120 wavelength step in one mirror that permits the observer to take readings accurate to 0.002 fringe, very much better resolution than any other experiment of his type. The interferometer is stopped at each orientation, and the observer adjusts the instrument with small weights to center the image. The number of weights was calibrated to give the reading for fringe shift. His use of a constant temperature room also reduced his systematic drift considerably compared to the other experiments. The interferometer was adjusted to 0 before the start of each turn, so the initial reading at north has a 0 error bar. This also makes determining the overall systematic drift impossible. Okay, so this is, and let's get down into the graphs because this really helps, just visualize it. So this is a page from Miller's actual data. Again, Ether Physics 101, this is what we were talking about. We're talking about how Miller used the interferometer to record variances in the speed of light, which he then correlated to the sidereal calendar. And here you see him plotting his sinusoid, wave pattern based on his calculations that he's got up here. Again, this was before computers, so he was doing it all on notepads. It's kind of cool to see. But anyway, this is the data set that Tom Roberts was reanalyzing. Okay, here's the raw data from figure 1. And here you can really see the systematic drift that he's talking about. That, when you start the run, it's, up here, usually a fringe in one direction, but you see that the fringe varies. It basically moves almost up to 6 fringes in the other direction over the course of the run. And this was a very consistent thing, and it's very interesting. They, in their analysis, a lot of these relativists, they analyze this, and they'll say, oh, that's an error, right? Why is this systematic drift happening? It must be an error. And I have my own, minor hypothesis about that, which we'll get into in a second. But let's just cover the graphs first. Okay, so that was the raw data from figure 1, essentially, so that's figure 1, this is figure 2. All right, here's figure 3. This is the assumed linear systematic drift It's kind of just, averaging out a little bit that systematic drift. Here's the most important one, right? So this is figure 4, the plot at the bottom of figure 1 with error bars. So he's saying these little dots are the signal that Miller recorded, and this is what, Miller was claiming shows us the absolute motion of the Earth. And here, these bars up here are the error bars that Tom Roberts has calculated using all those methods, just, exhaustively explained to get these error bars. And you can see visually what he's trying to say, that, see, the signal is so small compared to the error bars that you can't say that that's anything statistically significant. However, let's look a little bit closer at this graph. What is the error bar value that he's putting on here? You can see, all right, so we're in between 0.5 and 1 here. That's the 0.7 or 0.8. As you can see, they vary a little bit, but essentially 0.8, right? So he went with one of the 3 different values that he gave, again, the cosine and latitude, whatever the hell he's talking about there. If that's how he got it, I'd like to know more of what that actually is. But again, he went with the highest of the 3 values and didn't fully explain why that's the correct value. He gave other values which were way down here, right next to these dots. Okay, there's frequency, here's the Fourier analysis. So basically, again, reducing all of the data, as in what the fringe was and what position the interferometer was around the circle, and they reduced all that to this Fourier analysis. I'm not a statistician, I'm an English major, okay, I'm just reading about this stuff, and I'm smart enough to understand what they're talking about. And so he says frequency bin 40 has a period of half turn where any real signal would be. And sure enough, you see right there, it's not huge, but it's definitely a discrete signal. That is definitely an outlier in that set. There's a specific reason why that one is there. So again, he's admitting that there is a signal. He's admitting that it was detected. He's just saying that it's not big enough to matter compared to the instabilities, which were also recorded. Here's more frequency stuff. All right, frequency bin 2 has a period of half turn where any real signal would be. Well, it looks like there's a pretty clear signal right there. Here's another one. Here's another one, frequency bin. Any real signal is in frequency bin 1. And here you see a big old signal right in frequency bin 1. So this is the thing. He has made a very convincing and persuasive, highly statistical article, breaking it all down using computers and supermath, right? But his own charts are not entirely clear. They don't entirely correlate to his article. And also the graphs also seem to suggest that the signal was measured and is very statistically significant. So, that leads me to, have slight skepticism and question about this guy's, motives. Again, he acknowledges at the beginning that how people think about Miller's result is for the large part ordained by their existing prejudices. And I'll admit it for myself, I've seen the ether at work. I make orgonite, right? I've seen how the orgone field affects weather patterns, how it affects human biology, and I'm not going to disbelieve my eyes and my own experiments if they contradict relativity just because relativity is relativity. If my experiment and my experience and my tests and my eyes show that relativity is wrong, then relativity is wrong, okay? And that's led me down this path. I am willing to be proven wrong, but if somebody's going to say that I'm wrong, they're going to have to explain all the things that I've brought to the table, right? So, and here we go, basically, here's another sidereal time mapping of it. You can see the instabilities, yes, they are far out, and, a lot of the normal measurements are very close to 0. So, but you can see, so this is 24, I believe those are months, right, sidereal time. So, right, you can see a sort of wave pattern over it, especially with regard to the instabilities. But anyway, so yeah, and here's him doing that same with the Michelson-Morley. The Michelson-Morley data was very, very inferior to the data of Miller. Miller got a ton of data, and that's why this guy Tom Roberts was able to analyze it as such. And there's from the Illingworth data. Right, so that is what we're talking about with regard to what that viewer brought forward as the most effective rebuttal to my video, Ether Physics 101. And I will agree, it is a very persuasive article. It makes a very strong claim, but I've read through it, and this is the weak point in the article, is this graph right here. This is the visualization of his entire claim, and again, it does not match up with the data presented in the article, or at least if it does, it's not fully explained, and that's on him, not on me.